Okay, so we are talking about elementary row operation, and we will see how that will be useful for finding the rank of a matrix. So, there are basically three types of elementary operation, either on row or column. So, first one is to exchange two rows or two columns, like ith row is going to exchange with the jth row and the ith column is going to exchange with the jth column. And the second operation is we have a row, ith row, and that we are multiplying with some scalar, some real number, another real number, field element, and that will be replaced by that. And similarly for the column, and we have another elementary operation is like we have a we are replacing the ith row by ith row plus some constant some scalar into the another row. So, that is the another elementary operation, and that will be similar for the column operation. So, that there are three types of elementary operation we are considering, and this will be useful for finding the rank of a matrix. So, just we will see how it will help us to find the rank of a matrix. So, let us consider an example where we will apply these row operations on column operations to get the rank of a matrix. Okay, so actually we will take some matrix. So, suppose we have a 4 by 4 matrix 2 0 4 2 3 2 6 5 5 2 10 7 0 3 2 5. Suppose we have given this matrix and we have asked to find the rank of this matrix. Okay. So, one way to find the rank of the matrix to check the all possible minors. We can check the determinant of this, that is the minor of order 4, and if it is non-zero then rank is 4 and it is a non-singular matrix. Now, suppose it is 0, in fact it will be 0 I think. So, it is 0, then we have to go for checking whether rank is 3 or not. So, for that we need to check all possible 3 cos 3 submatrix and take their minors, take their determinant value, that is the minor of order 3, and then. So, this is the way, but we do not want to go into that way, because that will take some time to get the all possible minors. So, on the other hand we will just do the row operation and column operation to reduce this matrix to a row reduced echelon form, what we say. So, we will just apply row operation and we will try to get some identity kind of matrix over here, some 0 and 1, that is the normal form of the, that is called row reduced echelon form. So, we will say okay, we will come to that. So, now if we apply this, we will try to apply some row operation on this matrix and we try to get the matrix which is contains 0 and 1. So, we will just do R 1 is replaced by half into R 1, this is the one row operation. So, then this will be reduced to this matrix. So, we just divided by half. So, this is 1, this is 0, this is 2, this is 1. This is 3 2 6 5, 5 2 10 7, 0 3 2 5. Okay. Now, if we subtract this with if we multiply 3 with this and subtract with this, then this may get 0. So, we want to find, we want to get all zeros other than this. So, we want to basically the idea is to get the kind of identity matrix. So, that is the standard normal form, row reduced echelon form. So, if you do that, so if you do this R 2 is going to, this is another elementary operation, R 2 minus 3 R 1. So, we are going to replace R 2 by, we are multiplying 3 with this and then subtract with this. So, then it will be, so only R 2 is changing. So, row 1 will be remain same, row 2 we are multi, so this will be 0 then, and then we are, this is 2, this will be remain unchanged and this is 3. So, we are multiplying 3 with this. So, this will be again 0 and we are multiplying. So, this will be 2 and remaining things will be unchanged 2, 10, 7, 0, 3, 2, 5. Okay. So, now this matrix we got by applying the row operation, elementary row operation on this. So, that they are called row equivalence. So, two matrix A B will be the row equivalence if we get A to B by applying the elementary row operations. So, this is our A matrix. So, this is our B matrix. Now, we are getting B by applying elementary row operations. So, then we say they are row equivalence matrix or row reduced matrix. So, the idea is we are going to replace this matrix, we are going to keep on apply the row operation on this matrix and we will try to get the similar to identity matrix on this. Okay. We want to have only 0 and 1 and we want to try to fit the 1 in the diagonal element and the remaining element all will be 0 if it is. So, that we are going to do. Okay. So, similarly, we can just apply the again we apply the row operation on this. So, now this we are going to change. So, we multiply 5 with this. So, this is R 3. So, if you do the R 3 is going to replace by R 3 minus 5 into R 1. This is another elementary row operations. Okay. So, this if we do then it is becoming, so only R 3 is changing. So, we take the 5 then this is become 0 and then we take this is 2 and we multiply it by 5 with this. So, this is again 0 and 5 with this is again 2 good. So, now this will be remain unchanged. So, this is again we apply the another row operations on this. So, this will be So, these two if you subtract these two row then 1 will be 0. So, what we do R 2 is going to replace or R 3 any one of this R 3 is going to replace by R 3 minus R 2. So, if you do that then this will be 0 because these two rows are identical 0 2 1 0 then R 3 we are replacing 2 then these are all zeros 5. Now, we want to keep this zeros row in the end. So, that for that what we do we exchange these rows, we exchange R 3 and R 4. So, if you do that we will get 0 0 2 1 then 0 2 0 2 then 2 3 2 5 then 0 0 0 0. So, we are going to exchange the R 3 and R 4 with this. So, we reach to there and if we do the further row operation on this matrix. So, this will be eventually like this matrix only row operation we are doing 1 0 0 minus 1 0 1 0 1 0 0 1 1 0 0 0 0. Okay. So, again after this we can replace this row by we can divide it by half, we can multiply with half with this row. So, this will be like this, then we can multiply with this. So, this will become, this will vanish like this we can do, then eventually this will be of this form. So, this is the row equivalence and this form is called row equivalence echelon form. And from here we know that if we have a matrix A and if we have a row reduced matrix then their rank is same. Why it is? We will see that. We will see that if we apply row operation, this is similar for column operation also. If we apply row operation on a matrix, we will get another matrix. Now, this rank of these two matrices are same. So, we will discuss why it is so. So, if the rank of these two matrices is same, we can easily verify rank of this matrix is 3, because this is a minor of order 3, which is non-zero, and this is a minor of order 4, this is only one minor of order 4. So, rank of this B matrix is 3, and this is the row equivalence with A matrix. So, rank of A is also 3, but the question is why they are same, why if we have a matrix and we are getting another matrix by applying the row operation or series of row operation, then the question is why their rank is same, that we have to do that. So, for that we need to bring the concept of elementary matrix. Elementary matrix means, so this is the row operation we are doing on this is nothing but if we apply the same row operation on the corresponding identity matrix and we are multiplying that corresponding that is called elementary matrix. We are multiplying the corresponding elementary matrix in the prefix of that, and that is, so we will come to that. So, like yeah, let us take these two row operations. So, yeah, I will come back to this. So, now let us define what do we mean by elementary matrices. So, what is the elementary matrix? Now, we have three types of elementary operations. One is we are exchanging the rows or columns. Okay, first we talk about rows on rows. Yeah, we are considering the elementary row operations. Okay, so what is the elementary row operation? There are three types of elementary. First operation is like exchanging the ith row and jth column. We have a matrix A, and this is A11, A1n, and we have AI1, AIn, dot 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 AJ1, AJn, like this. Now, this operation, so this operation means we are exchanging the ith row and jth column. Now, this is same as if we have a identity matrix, corresponding identity matrix 1 0 0 0 1 0 like this 0 0. So, for ith, so we are doing the same operation on this. So, R I j. So, this is converting, this is denoted by E I j. So, E I j means we take an identity matrix of the order is same as the order of the row, and then if we exchange the ith row and jth row on this, that will become E I j. Now, doing this operation is nothing but multiplying E I j with A. So, this will give us, this is nothing but R I j. So, this we can easily verify this. So, we just instead of doing the row operation, elementary row operation, we just take the identity matrix, we apply the corresponding row operation on this identity matrix, and then we multiply prefix, we multiply with A, that will give us the corresponding row operation, elementary row operation. Okay. Similarly, for other two row operation is also same. If we want to multiply, say if we are going to replace R I j by some constant alpha R I, what we will do? We take the identity matrix E of size n by n. Now, we apply this row operation, R I is going to alpha R I on this identity matrix, and we got a this E matrix. This is elementary matrix. This elementary matrix is denoted by I plus alpha, sorry, I alpha I we can say, we are multiplying alpha with this. So, now doing this operation on A is same as we just multiply this identity element, this is called elementary matrix under this corresponding elementary operation. So, we will just multiply this with A and that will give us this elementary operation, that R I is going to alpha R I. So, the doing elementary operation, elementary row operation is nothing but multiplying this elementary matrix with the matrix A prefix way. Now, since this is elementary matrix and elementary matrix is non-singular matrix. So, that means that means their rank will be same. So, if we have a matrix A and if we are doing the row operation on that, we are getting another matrix B, that is nothing but multiplying the elementary matrix with A. So, then the rank will be same. So, that is why the rank of this is same. So, if you have a matrix A and we are getting another matrix B by doing the elementary row operation. So, that this is nothing but we have a we have some elementary operation E1, E2, EL say L times, we do not know. This is becoming B and these are all elementary operations, okay. And these are all non-singular matrix. So, say that is why rank. So, rank of A is same as rank of B, and this we can denote it by P matrix. So, P A is equal to B, where P is a non-singular matrix and this is called row reduced echelon form. So, P of P is this, okay. Now, we can apply the corresponding column operation also, then it will giving us the column reduced echelon form. So, but the column operation is corresponding elementary matrix, we need to multiply the after A. So, for column operation, so for elementary column operation, so what elementary column operations are? First operation is Cij, that means we are exchanging Ci with Cj. We have a column, this is ith column, this is jth column, we are exchanging these two, this is our A. Now, this is same as if we get the corresponding elementary matrix, that means we take the identity matrix 0 0 0 1 0 and size of this matrix is the number of columns over here. So, if we just exchange the ith column and jth column, so if we do the Cij on this, so we get corresponding Eij, okay, or for column we can denote the Fij. Now, if we multiply A with Fij, this will give us these operations. This is nothing but Cij, we are getting another matrix P. So, this is this for column operation, this multiplication is from the right side, and for row operation this multiplication from the left side. So, if we apply only column operations on this matrix A, so eventually we will get a equivalence column equivalence echelon form. So, we have a matrix, we are keep on applying F1, F2, FL say. So, we will be getting this. So, these are basically the elementary column operation on this. So, this is if we denote this by Q. So, AQ is equal to B. So, that means, so this is the column equivalence, because we are applying elementary column operation on this. So, applying elementary column operation is nothing but multiplying the corresponding elementary matrix from the right side. like this. Okay. So, now we can have a normal form of this. So, if we are doing both row and column operations, suppose we have a matrix A whose rank is a m by n matrix, or for simplicity we can take n by n. Suppose rank of this matrix is, for simplicity we can take this. So, rank of this matrix is A. Then if we apply the row column operations, if we apply row operation, it will reduce to a row reduced echelon form. Then again if we apply the column operation, it will reduce to a column reduced echelon form. So, this way, so applying row operation means we multiply the elementary matrix, row matrix in the prefix, and apply column operation elementary column. So, basically we will have A. So, this is the elementary row operation we are doing, say k times, and this is elementary column operation we are doing, say L times. So, this will give us the normal form of the, this is the 0 0, this is the 0 matrix. Okay. So, this is our P, this P, these are all non singular matrix because these are elementary matrix. So, we have P A Q is equal to this form. These are all sub matrices. Okay, this P is nothing but the product of the elementary row operations, elementary row elementary matrices, and Q is nothing but the product of the elementary column matrices, and they are non singular. Okay. So, this way we can proceed. Now, suppose A is non singular, A is a square matrix, and suppose A is non singular. So, that means rank of A will be n. So, that means we have a 2 matrix PQ. So, similarly, so this will be nothing but identity matrix fully I n. Okay. So, now we got P A Q is equal to identity matrix, because this is the row operation we will do, the column operation we will do, and eventually we will get the form. So, what is then A? So, we will just do the inverse of this. So, P is a non singular matrix, Q is a non singular matrix. So, A is, so yeah. So, actually we want to get the inverse of this, inverse of A inverse. So, A inverse is nothing but if you multiply the P inverse over this side. So, so A is nothing but P inverse Q inverse like this, because if we multiply both sides by P inverse P A Q, Q inverse, this is P inverse Q inverse, because that is the identity matrix. So, this will give us A is equal to P inverse Q inverse. Now, if you take the inverse of this, so this is nothing but inverse of this. So, this is Q P. So, this is the inverse of a non singular matrix. So, that is why how to get the inverse of a matrix, this technique we used to do. So, we take a matrix A and we take an identity matrix. Now, we apply the row operation and column operation on this. So, that will give us basically this PQs, and once this became non singular matrix and this is B, then this is the inverse. So, we keep on applying row operation column operation on this until this becomes the identity matrix and this became this B. B is the inverse of this, then this will be inverse. So, this is nothing but we are doing the multiplying the PQ. So, that is why this will work. Okay. So, this is the way we find the inverse of a matrix. So, now just to give a quick example, we can just yeah, let me check whether I have a example of no. So, I want to take the this normal form. So, suppose we have a matrix 0 0 1 2 1 1 3 1 0 3 2 6 4 2 3 4 2 8 3 9 4 2 10. So, we want to find the rank of this matrix, and in particular we want to get the this normal form of this matrix. If the rank is R, we want to write this in IR 0 0 0 kind of things. Okay. So, that is the fully reduced normal form. So, we have to do the row column operations. So, I am not going to the details of this. First, we will do this R 1 2. So, we are exchanging this row and this row. So, that is same as we are multiplying the elementary row operation on this. That means, we take identity matrix, we will do the same exchange on that identity matrix, that will give us elementary matrix. So, doing the elementary row operation means multiplying the elementary matrix before that A prefix. Okay. So, this if we do, then eventually we will be getting. So, we will be getting a matrix, then again we have to do this some row operations. So, we will first try to do the row operation. So, if you do continue this, eventually I am not going to details of this, you can just work out the example at home. So, only doing row operation we can reach to this level 1 3 0 0 2 0 0 1 0 1 0 0 0 1 0 0 0 0 0 0. Okay. This is the row reduced echelon form, and this we are getting only by row operation. This is a B. So, A is row equivalence to B, row equivalence. So, this is the row reduced echelon form, but we want fully normal form. So, now it is time to. So, up to this we achieve by only the row operations. So, that means, up to this we achieve by multiplying the elementary matrix prefix way. Now, we have to go for column operations also. So, now we have to apply the column operation. How we will do that? So, if we just take this column. So, idea is to convert into this type of matrix, equivalence matrix. Okay. So, now we can take this column and this column, these two columns are similar. So, we can just make it 0. So, C 2 we can replace by C 2 minus C 1. If we do that, then these are all zeros. So, we can just write that. Yeah. So, from here we can just do C 2 is going to C 2 minus C 1, then this first column will remain same, this will be all zeros, then 0 1 0 0 0 0 1 0 2 1 0 0. Now, we can exchange these two column. In fact, we can exchange these two column, then we multiply this with this. So, by doing another column operation, we can reach to this I 3. So, I 3 means 1 0 0 0 1 0 0 0 1. This will get 0 0 0 0 0 0, and then we have another zeros over here. So, this is our I 3 and this is a 0, this is a 0. So, this is the fully reduced normal form, and this we can achieve by applying another column operation over this. Okay. So, any matrix can be reduced to the fully normal form of this. If the rank is here, rank is 3. If the rank is R, it will reduce to IR 0 0 0 by applying both the row and column operations elementary. So, both the row and column operation means P is coming from row operation, Q is coming from column operation. Okay. So, that is the. Thank you.